Welcome back one more time. We've looked at an electronics problem from the matrix solution approach. This time we're going to look at it using Cramer's rule and see how much more quickly we can solve it with Cramer's rule than we did with the matrix algebra approach. So here's the circuit we've been working on. We have 3 resistors, 2 power supplies, and our challenge is to find what the currents are that are flowing in each of these loops. We've set the problem up, we've solved it using matrix algebra. This time we're going to solve it using Cramer's rule. Okay, let's put the pieces in place to use Cramer's solution. We know that our matrix A times the unknowns is equal to B, which in matrix format comes up looking with a 2 by 2 for A 1 by 2 for the unknowns, and a 1 by 2 for the result vector. But when we're dealing with the unknowns, Cramer tells us that a revised version of matrix A, substituting the B matrix into the first column, will give us the result of the first unknown. Similarly, substituting the B matrix into the second column will give us the second unknown when we divide the determinants of these matrix by the determinant of the original matrix. Again, the same thing. Divide this matrix, the determinant of this matrix, by the determinant of the original matrix to find our unknowns. Solving for the first unknown, we'll take and create an A1. So if the determinant of A is A11 times A22 minus A12 times A21, we find that when we put the B matrix in, instead of A22, now we have B1 and B2, so we have A22 times B1 minus A12 times B2. And that becomes the determinant of our A1 matrix. So that X1 becomes the determinant of the A1 matrix divided by the determinant of the A matrix. Similarly, solving for the second unknown, we'll do the same thing. If the A matrix, the primary matrix, is A11, A22 minus A12, A21, we substitute B1 and B2 in place of the second column of our matrix. So this gives us our new set of equations to solve for our second unknown. If this is our A matrix, which it was, with 1210 in the A position, minus 390 in the B position, minus 390 in the C position, 590 in the D position, and our result vector is minus 4.3 volts for the I1 loop and minus 7.9 volts for the I2 loop, then our determinant, which we've already calculated, is 561,800. Substituting values, our determinant for the A1 matrix becomes 5618, again negative, and A2 becomes a minus 11,236. So when we do the divisions, and I've simply replaced here with the I for any matrix, now we've got X1 is minus 5618 over 561,800, which is minus 0.1. X2 minus 11236 over 561,800 gives us a minus 0.2. Now we look at the results. We calculated that I1 was a minus 0.1, I2 was a minus 0.2. which agrees with what we found when we did the solution using the matrix method, and that tells us exactly the same thing. The current was flowing in the opposite direction that we expected it to flow. So both cases, it's flowing in a counterclockwise direction. This brings us to the end of our analysis of systems of linear equations. We've looked at 4 different techniques for solving a linear equation. We've solved 2 problems, one in mechanical, one in electrical engineering, to show application to some specific physical world examples. I hope this lecture has been helpful. This series of lectures has been helpful as you begin to look at what you can do with systems of linear equations. And now it's your turn.